Okay, so this is group 1, and we are presenting on evolutionary algorithms. Mr. Pascal will share the screen, and Mr. Ziam would quickly take us through what we intend to do for this session. Mr. Ziam, are you online?
Yeah, give me a second.
Okay, sure. That's fine. Okay, so Mr. Pascal is actually doing a test run of the code whilst we prepare for Mr. Ziam. And yes, so yeah, so we can actually see what we have to deal with today and the actual result also. Okay, so let's proceed.
All right, so at this particular point, we are trying to solve a real life problem using the evolutionary strategy algorithm to find a real life problem, solve a problem. And one of the problems we have come across is the traveling salesman problem, the TSP. And we want to write a Python code that can eventually solve this particular traveling salesman problem. And the code provided implements a simple evolutionary strategy algorithm to solve the traveling salesman problem. The goal of the TSP is find the shortest possible route that visits all given cities exactly once and returns to the starting city. In order to write this code successfully, we have to implement import some libraries, some very important libraries. And the first is the random library, which is used for generating random numbers. And there's another library called the math library, which provides mathematical functions. It uses the math.hyport for calculating the Euclidean distance between two points, in this case, two cities. We also imported the NumPy library, which is an essential and widely used library for Python for numerical computing and data manipulation. So after successfully importing these libraries, the first function we want to define is the fitness function. Now, this fitness function takes a route as an input. It takes a route as an input. We are dealing with routes here from one city to the other. We are going to use routes. So it takes a route as inputs, which is represented as a list of 2D points, 2D cities. It calculates the total distance traveled in the given route for the traveling salesman problem. So if we are moving from city A to city B, and from city B to city A, or city A to B to C and back to A, this is what this particular function does. The function iterates through each city in the route and calculates the distance between the current city and the next city, wrapping around to the first city for the last city. It uses math.hyport to calculate the Euclidean distance between 2 points. That's the function, the fitness function. This is what it does. Then we define this other function called the general random route function, which takes a list of cities, and in this case 2D points, as input and returns a randomly shuffled route list of cities. So how many numbers you are given to, you are inputting into this function, it takes that number of cities or inputs, it shuffles them, and it produces a result according to a certain linear. This function is used to create the initial parent population in the evolutionary algorithm. Now, after we have successfully implemented or defined this function, we go to define another function called the recombination or crossover and mutation function. This function is a bit huge, and it does some very important functionalities here. The recombined function performs a cross combination operation between two parents. It takes a parent 1, it takes a parent 2, it randomly selects elements from these parents to create two new children. So we have a child 1 and a child 2 too. So two parents, some elements of these parents are put together to create two different new children, child 1 and child 2. This recombination process is used in the evolutionary algorithm to generate new offspring from selected parents. The mutate function, which is part of this particular recombination and mutate function, takes a child, which is a representation of a tuple, and randomly swaps some of its elements, some of the elements of this child with a low probability mutation rate. This is a mutation operation that introduces small random changes to the offspring to explore the solution space better. Now, after we have been able to do this, there's this other function that is super important, and it is called the 2-opt local search. The 2-opt local search function represents the 2-opt local search algorithm, which is a local optimization technique used to improve a given route for the TSP problem. However, you can implement the 2-opt algorithm to further refine the solution obtained from the evolutionary algorithm. This particular function comes in to refine, especially when you are running your code, but you are not getting the expected result. As in, before we got this particular function introduced, our code was running, but we were not getting the desired result. It was returning the same the series in which we present our cities, and our route, our ultimate route, we were not getting the value that we needed. So we implemented this particular function, and this function takes the result, refine the result, and produce a better result. Along the way, you see the outcome, and you know what exactly this function does. Now, after this particular function, we also define the evolutionary strategy algorithm. And this particular function implements the evolutionary algorithm for solving the TSP problem. It starts by initializing a random parent population and then proceeds with generating offspring through recombination and mutation, as mentioned earlier. In each iteration, the fitness, which is the total distance, in this content, anytime we are talking about fitness, we are talking about the distance covered, because we are dealing with cities. We are talking about the distance. So in each iteration, the fitness, which is the total distance of each offspring, is calculated using the fitness function, and the best route, which is the lowest fitness, the best route here is the lowest fitness, is updated if a better offspring is found. Finally, the function applies 2-opt local search to further refine the best route and return the best route and its fitness. As I was explaining earlier, after you have gotten your solution, the 2-opt local function takes this solution, further refines it, finds the best route, and returns it in its fitness. So it's going to give you, according to the cities that you are going to use. If you are going to move from city A to city B to city C to city F, before you come back to city D, it's going to give you that kind of arrangement to know how short the distance is going to be. Now, finally, we have this main function that we define, which is the main function, and it creates a sample cities of list 4. In this case, our cities are 4 cities. We just provided 4 cities. So it takes this list of 4 cities. It then calls the evolutionary strategy algorithm function to find the best route, that is the shortest toll, and prints the order of cities in the best route along the total distance traveled. So this main function is going to take this cities as you have presented, shuffle them, find the best route, and find the shortest distance. Now, one thing we need to take in mind is that the evolutionary algorithm is stochastic, meaning the results may vary between different runs. Running the code multiple times might yield different best results in total distances. That is the issue with this particular evolutionary algorithm. So if you don't understand it and you run it for the first time and you run it for the second time, you're expecting the same results you're not going to have, because anytime you run it, it's going to produce different results and different arrangements. But it is assuring you that every time, whatever it produces as a result is the best outcome for you. So in running, if you look at the code now, we run it the first time. This is what we have: best route order. We have one, yes, scroll down, let me see. We have 1, 0, 3, and 2. This is the best order in which, if we are to travel, we go from city 1, you go to city 0 to city 3 to city 2. And you're going to have your distance travel to be 8.485 and whatever. If you run it again, it's going to give you a different arrangement. And if you run it for the third time, you're most likely going to get a different arrangement, exactly what is happening now. Before we had 1 and 0 something. Now we're having 3, 0, 1, 2. And we're having the total distance to be different from the first. If we run it again, it's going to give a different arrangement. But in all this, we are assured that whatever the code is producing is always the best at this particular time that it is giving us. And this is how we have been able to solve a real life problem by using the evolutionary algorithm strategy. So this is the end of our presentation in code. Thank you.
Thank you, Mr. Ziam. Thank you, Mr. Pascal.